This is the connected engineering ecosystem workflow, a step-by-step journey that mirrors how real engineering projects evolve. We begin with step one, where stakeholder requirements arrive from multiple sources: engineering documents, safety standards, customer specifications, and regulatory guidelines. They often come in different formats, and this step is all about capturing and understanding them clearly. Next, in step two, we move into system architecture and behavioral simulation. Here, system engineers and requirements engineers collaborate to define behaviors, analyze scenarios, and validate early functionality, ensuring that the system is conceptually sound before any implementation begins. Once the system behavior is well understood and validated, we progress to step three. From the designed architecture, we generate high-level C++ architectural code, which becomes the foundation for the next development phases. Then comes step four, where the focus shifts to running, debugging, and validating the solution in the actual embedded environment. This includes build management, performance optimization, runtime analysis, and ensuring that the code operates reliably under real-world conditions. After that, we enter step five, which covers static analysis and unit testing. This step strengthens quality, improves coverage, and ensures compliance, especially crucial for safety-critical domains like automotive, aerospace, and medical systems. Throughout every step of this workflow, traceability remains seamlessly connected. So if a requirement changes, a design is refined, or a test reveals issues, the ecosystem instantly shows what is impacted, enabling quick updates and confident decision-making. Together, this creates a closed-loop engineering ecosystem. Not just a collection of tools, but a unified, connected workflow that accelerates development and improves product quality. To understand our solution, we'll walk through a use case: airbag control system. Here, we have different types of inputs flowing into the control logic: collision sensors that detect impact, seat occupancy sensors that determine whether the passenger seat is occupied, and basic vehicle state information like ignition status, diagnostics, and speed. The airbag control unit evaluates these inputs. If the impact is severe and the seat is occupied, it issues a deployment command. If the situation is less severe, it may simply trigger a warning lamp instead. We'll use this system as our reference scenario as we step through the demo. To understand this connected engineering workflow, we start with the stakeholder needs captured in Excel. These needs usually come from customers, standards, regulations, and system expectations. They are often scattered, written in natural language, and difficult to manage. By importing them directly into CATIA Magic, we make them part of the model from the very start. Each need is automatically assigned identifiers, description fields, and attributes. This gives us a clean baseline and ensures that every expectation is captured clearly. After collecting the stakeholder needs, we model these needs inside CATIA Magic using the Magic Grid framework. In the problem domain layer, we define the requirements, the context diagram, use cases, and the conceptual subsystems. Let's start by looking at the stakeholder needs. These are the same needs we captured earlier in Excel. Here, they appear as a requirement table, represented using SysML. Next, we move to the system context diagram. This helps us understand who the stakeholders are and how they interact with the main system. For example, between the vehicle occupant and the airbag system, there are two key interactions: safety information and seat occupancy data. Each stakeholder has similar interactions defined with the airbag control system. With this understanding, we build our use cases, which describe how the system provides active safety and airbag protection to the vehicle occupants. We then perform a functional analysis to identify what the system must do and what system requirements need to be written. Let's simulate this functional analysis to understand the flow. Under the vehicle subsystem, we have ignition information and vehicle speed. From the sensors, we receive collision data and seat occupancy status. The control unit performs diagnostics and calculates impact severity. Outputs are sent to the actuator and display, while a storage device records diagnostic data. When we simulate this, you can see how data flows from the sensors into the system and how the control unit processes that information. For example, if the input conditions indicate a severe impact and the seat is occupied, the system triggers deployment and sends a notification to the user. After functional analysis, we define the interfaces for the airbag control system, including speed, ignition, storage, display, and other subsystem connections. This interface model shows how signals flow between subsystems of the airbag system. For example, vehicle speed flowing into the control unit, sensor data entering the system, and the deployment or warning signals leaving the system. Next, we define the system-level requirements for the entire airbag system, describing what each subsystem must do at a high level. Based on these requirements, we derive the system behavior using a state machine. Let's simulate that state machine. During simulation, you can see how each behavior is linked back to its corresponding system requirement. For example, when the correct input conditions are met, the system transitions into the deployment state and the airbag is activated. With system behavior validated, we now write the subsystem requirements for the controller unit. We have around 7 requirements defined for it. But to ensure that these requirements are correct, complete, and consistent, we validate them using the stimulus tool. Stimulus checks the logical correctness of the requirements and confirms whether the specified behavior meets all conditions without conflict. This is the stimulus interface. Here you can see the glossary that defines all the input signals captured from CATIA Magic. We've also imported the system requirements from CATIA Magic and rewritten them in a formalized structure using the stimulus library templates. Now, let's simulate these requirements using the input signals and the safety observer. One of our key safety rules is that if no collision is detected, the airbag must not deploy. So we will run the simulation and check whether any conflicts or gaps exist in our requirements. As you can see, stimulus immediately highlights missing gaps, undefined conditions, and conflicting requirements. It also provides detailed error messages so we can inspect exactly where the issue occurs. We can navigate directly to each requirement to understand what caused the conflict, and we can also view the timeline values to see for which inputs and at what timing the conflict happens. When something is wrong, the safety observer turns red, indicating a violation of the intended behavior. To address these issues, we refined the requirements and created version 2. In this updated set, we added 2 additional requirements related to diagnostics to cover all missing conditions. Let's simulate the refined version. Now, when we run the simulation, you can see that we are no longer getting any requirement errors. Stimulus confirms that the requirements are now correct, consistent, and complete. With the validated requirements, we return to CATIA Magic. Here you can see that the validated set is now imported back into the model. Using this validated system behavior, we then created the class diagram identifying key functions and reusable components for the embedded target. With the support of the code engineering tools, we can generate the corresponding C++ files directly from the model. Once generated, the files can be taken into Green Hills for the implementation phase. These are the generated files that will be used for the actual embedded development. Here we have the hardware setup consisting of the Green Hills probe, the STM32 evaluation board, and the teapot. So now we will move on to the Green Hills Multi, where we can compile and debug the architecture-generated code produced from the CAT image. This is a multi-project manager of the Green Hills tool, and under the source program, we have imported the generated source code. First, we will build the project, and build has been successfully done next. Let's debug the code. So now we are in the debugger window. We will connect it to our target board, which is STM32 evaluation board. So the target has connected successfully. Now we will download our code onto the target board, and the download is complete. And now we are in the debugger view. We have a lot of features in the debugger. Here, this is the list of features. Now we have the register view, where we can see the processor register value. And we have the call stack. It will show the sequence of active subroutines. Then we will run our software. The program contains an infinite loop, so it keeps on executing continuously. After some time, we will halt the execution. Once it is done, we can see the updated call stack, and the assembly instructions and the register values. So these three windows remain synchronized. The call stack that execution started from the main and which matches the current view in the main window, then it is followed by the airbag control unit, so it doesn't serenade. We can observe the same flow in all three panels. So here in multi, we can do the reverse debugging, allow us to step backwards through time, essentially going back on previous instruction. For example, we can step back from .syscall and then .syscall 64 and host.io write and then fls-buff all the way back to the start of the execution. Observe the register values at each instructions. We have one more feature called trace list feature. So the trace list provides a detailed view of the entire source code execution from the start to end. Functions are displayed in a parent-child hierarchy, showing the call relationships and the execution duration for each function. See, for example, here, if we select monitor sensor input function in the right side of it, you can see the address of it, then assembly instruction, opcode, then whether it has been executed or not, and then total execution time. At the bottom, we have a timeline view. Clicking anywhere on the timeline automatically navigates to the corresponding function, and the detailed things, we can see it in the right side panel. So we have one more feature called Profile. In the window, we can see the total execution time of the entire program. For example, here, the program took 6.987 seconds to complete. And then we can see all the functions category, how many times it has been called, how much time in the percentage. And then we can see it in the source category as well. Then we can see the assembly addresses of each function by selecting any function in the profile view. It will be synchronized with the source window showing the exact instruction where execution took place. So we have one more feature called history. So in history view, we can see how much time it has been spent by each function. Here we can see the sequential execution order of our source code. Let us zoom it for a little bit to see what other functions are there. So here we can see the exact chronological sequence from the start. We will write one of the functions. We can see this function took the minimum of 400 milliseconds to execute, then average time, then the maximum time. Then we can see the total time duration in it. So then we can also set a custom boundaries so that allowing us to restrict the profiling to a specific region of execution. Within the selected boundary range, we can see the combined execution time of parent and child functions. So here we can see it took 74.9 milliseconds to run the parent and child in the boundary range. We can see what are the files are there and what are the functions in it. Here the monitor sensor inputs. This is in the history window. Then correct C, correct zoom. You can see all the parent and child. Then we can see how many times it has been called and then how much time in percentage. So we have seen the downside. We can see the timeline where it has been started, where it has been ended. So we have one more feature called flaming graph, where we can see the maximum execution time across the entire software. For example, now we can see there are like 5 functions with such significant runtime. We can see the maximum time of it, each one. Here we can see this is the time which has been took it for this function. So this helps to identify the maximum time has been taken for the functions. Then we have the one more option called advanced search. In the source code contains many functions. Searching manually becomes difficult. Using advanced search, we can directly jump into specific function. For example, if I'm searching a main, here we can see it will show the start and end time. In the previous flame graph window also, then we can see here the minimum, average, and maximum time of it. So with this, we have completed the compilation and debugging demonstration using GHS Multi. Now we will move on to the Parasoft for software verification. So here is the Parasoft tool. where we are going to generate unit tests and execute the test cases on the target board. On the left-hand side, under the SRC package, we can see all the source files that we imported from Green Hills. Before running the test, let me first show you the Parasoft test configuration. Parasoft provides standard compliance support for multiple domains, such as in Aerospace Pack D or 178C, in Automotive AUTOSAR, ISO 26262, MISRA C and C++, and Medical Device Packs. And then in Security Pack, we have CWE, OWASP, and so on. Here, I'd like to show the configuration done for our target board. Under Execution Configuration, we can see the hardware configuration settings used to connect to the STM32 target. We can build and run test cases directly on the embedded target. We can configure the similar settings to the simulator as well. Now, we will enforce our code as per the MISRA C++ standards. We have enabled a total of 272 MISRA rules. The analysis has now completed. If we go to the Quality Tasks view, we can see all the detected violations. For example, in the airbag control unit file, if we double-click a violation, it navigates directly to the corresponding line in the source window. Here on hovering over the issue, we can see the message data member type should be initialized. So now we can easily identify the MISRA violation. Parasoft automatically generates a static analysis report for us. In the report, we can see we have total of 29 number of violations and total final is analyzed is 17. And we can see the total lines of code scanned. And then we can see the category by severity as well. There are 5 violations that is in severity high. There is a 24 violation that is severity as low. Then we can see what are the violations in a detailed view in a file type. Then what is the violation for it? We can see it in here and then we can see the detailed view as well. On the left side, where it shows 0, it indicates that none of the rules were suppressed. The number 29 indicates the total number of MISRA violations found. We can see the line number, what is the violation in it. And then we can see MISRA rules as well. So now we will generate a unit test using Parasoft's automatic generation features. Parasoft automatically creates the test cases for our source files. Here it has been generating. We can see in the console that the test case generation has completed successfully. Here we can see all the automatically generated test cases. Let's select one test suite, collision detection sensor, and execute it on the STM32 target board. We will execute it on the STM32 target board, so the execution has started. And now it has completed. You can see on the left side, green indicates passed a test case, and then red indicates failed test case. Parasoft also generates an execution report. Let's open it. So here is the summary, shows 3 test case has been passed. 7 test case has been failed. Below this, we can view the coverage summary. For example, the collision detection sensor file shows 100% coverage because all test paths in that file were executed. Scrolling further, we can see each test case along with the pass and fail status and failure reason and line number of the failure. This completes the unit testing and coverage analysis using Parasoft. So far, we started from the stakeholder needs in an Excel sheet and in the last with test case generation in Parasoft. Now we have multiple artifacts spread across different tools. However, there is no traceability between these tools. Any change in one artifact does not reflect in the others. Impact analysis is not possible across the workflow. To solve this, we will move on to Rectify, which provides complete requirement traceability and impact analysis across all these tools. Now we are in the Rectify tool. On the left side, we can see the overall project quality, which is currently 85%. Below that, we have a color indicator. Green means the requirement is covered and has no traceability violations. Red means the requirement is not covered and contains traceability violations. On the right side, we can see all the artifacts collected from different tools, which Rectify brings together to build complete end-to-end traceability across the project. Stakeholder needs. These are the high-level requirements maintained in an Excel sheet. System and software architecture from the CATIA Magic tool. These architectural elements are traced back to the stakeholder needs. Validated subsystem requirements from the stimulus, they are traced to the architecture elements of CATIA Magic. Software design document, SDD, it is traced to the architecture. Compiled source code from the Green Hills. The source code is traced to both the system architecture and the software design document. Software verification test results from Parasoft. The test cases and results are traced to the software design document. Now let's see how all these links appear graphically. On the left, we have the stakeholder needs from Excel. For any requirement, such as a single element in the list, we can see the ID, the requirement text, whether it is covered or not. Next, these trace to the model elements from CATIA Magic. On the left side, we can see the stimulus requirements, which represent the subsystem requirements imported from CATIA Magic. Below that, we have the validated requirements generated from the stimulus model. By selecting any requirement, we can view its complete description along with all its traceability links. Above that, we have the software design document, which contains the algorithms for each function. When we select a function, we can see the detailed design description and whether the algorithm is covered or not, and its traceability to both the source code and the system architecture. We can also see the GHS source code organized by file and function. On the right side, we have the Parasoft test case results. By selecting any test case, we can view its attributes, including whether it has passed or failed. Since this graphical view contains many interconnected artifacts, it can appear complex. So, to make it easier to understand, we'll filter the view and show the traceability for just one requirement. You can see the complete chain, from the stakeholder need all the way to the Parasoft test case results. For example, if we take a requirement such as vehicle speed is greater than 20 kilometers per hour, and then change this value to a different constraint, the tool automatically performs impact analysis and shows all the artifacts affected by that change. Before making any change, we'll first create a snapshot of the current project in Rectify. The snapshot is created successfully, and at this point, there are no differences. Now, let's go to the CATIA Magic project, where the requirement text exists. Here we can see the deploy decision logic requirement, currently set to vehicle speed greater than 20 kilometers per hour. We will change the value from 20 to 20.1 kilometers per hour. We save the project after making the modification. Now, returning to Rectify, we reload the project. After reloading, we navigate to the modified requirement. You can see a red marker indicating that a change has been detected. The new value, 20.1, is now visible in the requirement details. To compare the old and new versions, we open the snapshot difference view. Here, Rectify shows old text, vehicle speed is greater than 20. New text, vehicle speed is greater than 20.1. This confirms the requirement change. Now let's generate the impact analysis report, where we can see all the documents affected by the requirement change. In the report, we can clearly see the modified requirement and text has been modified. The upstream impact points to the stakeholder need from the Excel sheet. The downstream impact, which includes the validated stimulus requirement, the corresponding section in the software design document, in this case, the calculate severity algorithm, the source code implementation, and finally, the test case result. Here it is calculate severity 1. These are all the documents and artifacts that need to be reviewed and updated because of the requirement change. Rectify also provides additional report generation features such as traceability matrix, analysis report, coverage summary, and so on. Let's generate the analysis report. In this report, we can see overall project coverage, which documents cover which requirements, number of requirements and their coverage percentage, undefined requirements, untraced requirements, detailed traceability paths. All required information is clearly presented in the final document. With this, we have completed the requirement traceability and impact analysis using Rectify.